So unless I'm forgetting, I think you guys have a project milestone due today. I'm not wrong about that deadline, right? Somebody? Nicole, are you saying, am I right with that?
Yeah.
Milestone? Okay. This one.
Other assignments in hard copy in Mallory's office.
So one hard copy to Mallory per group, and then email the TAs and myself with the PDF as well. So by 4 p.m. It's not really supposed to be a very tough assignment. It's just a 2-page write-up. And then after this point, some point probably over the weekend, we're going to we'll divide up each group among the TAs. That was said improperly. The groups will be divided up among the TAs. Your groups will remain intact. But each group will be assigned a TA mentor. So you'll be able to kind of have more close contact with one TA about your project from now on. Of course, you can ask the other TAs and myself as well. But we've found in the past that when each group has a TA mentor, you get a lot more attention, and it kind of makes the project move forward more easily. Are there any questions about this milestone before we start? Oh, thank you. Okay, so last time we got most of the way through proximal gradient descent. We ended with this example on matrix completion. We still have a bit more to cover with proximal gradient descent. And we've been a bit behind the last few lectures in terms of we haven't quite finished all the material. And so it's spilled over into the next lecture. We're going to try to play catch up on this one because the material I wanted to cover with the numerical linear algebra primer that's going to come after this is really not going to take as long, I think. So hopefully we'll catch up and we'll be back on the schedule after this lecture. So we learned this algorithm called proximal gradient descent. It was quite useful because it allowed us to solve with the same speed, at least in terms of the number of iterations required until convergence, the same speed as gradient descent, but it applied to non-differentiable convex loss functions. And we're looking at a particular type of, oops, wrong way, functions, which were decomposable functions, were the class that we were looking at, where we had a differentiable convex function and then a convex function that need not be differentiable. We're trying to minimize the sum of those two. And the case to keep in mind is when this serves as kind of a log likelihood or a loss or some kind of thing that we would encounter in a typical statistics or machine learning problem. And this is a regularizer or a penalty where we typically don't make them smooth but still convex. And we saw with this very simple algorithm that was motivated by the same kind of quadratic expansion idea we used for gradient descent, we could get we could converge at the same speed as gradient descent if the function were only smooth. And essentially all we do is we take a gradient step with respect to g. So that's this part here. And after that, we apply what we call the proximal operator, which is something that is defined only in terms of h, the non-smooth part. And it's defined up here. It's the minimizer of this problem. The point that's closest to its argument, once we scale the least squares term by 1 over 2t, and we add an h of z. So this proximal operator tries to keep us close to the gradient update for g while still making h small. So it's kind of a balance between those two terms. Okay, and the nice thing is that this proximal operator, as we saw, doesn't depend on g. It's only defined in terms of h. And it's also, we can do it in closed form for many examples that we care about. Right? Because usually the penalties we choose, even though they're non-smooth, they're typically not super complicated. And so we saw an example with the L1 penalty. Essentially, with any loss in an L1 penalty, any convex smooth loss in an L1 penalty, we can apply this iterative soft thresholding algorithm. We saw that. And the one that we are looking at now was the matrix completion problem. And so I'm just going to tell you what that was to remind you. This is a more complicated proximal operator. In this problem, we had something plus a trace norm penalty. And the something in the context of matrix completion is just a least squares loss to the observed entries of some matrix. We only observe entries in omega of this matrix Y. And the proximal operator we saw, right, involved a matrix soft thresholding. So it's kind of a generalized version of what you do in the L1 case and the vector case to matrices. We actually proved this in class. We didn't prove, the only part we didn't prove was that we didn't prove that there's a certain subdifferential of the trace norm that we could take for granted. That you're going to prove on your homework. So that comes from your homework. Besides that, we stepped through the proof. I think it was fairly sophisticated. If you didn't understand that, then make sure you go over it offline, or you can come to one of us and ask us about it. So how do you derive prox operators in general? Well, we know that, for example, for any convex problem, we can apply subgradient optimality. Right? If I want to know something like what is the minimizer of a problem like this, right, where this is some given non-smooth function but convex function h of z, then I can always take a subgradient of this and try to set it equal to 0. That's often the strategy we take for deriving proximal operators. So that's how we derived the soft thresholding operator when it was the L1 norm. We just did that several lectures ago. That's also how we did it here for the trace norm. And this part is differentiable, so we always just get z minus b here over t. So it's really just z minus b over t plus lambda times the subgradient, a subgradient of the whatever the function is we're trying to minimize, set that equal to 0, and that'll tell you what the proximal operator should be. That's what we did here. OK, and it ended up with a pretty nice algorithm called soft impute. People use this not at large scale, but this is pretty commonly used for, I'd say, moderate scale matrix completion problems. Okay, the thing that makes this difficult to do at scale is that it requires an SVD. This is an example of a proximal operator that's very expensive because the proximal operator, this S of lambda, it requires taking the SVD of its argument and then soft thresholding the singular values and then putting that back in. And then we leave the left and right singular factors alone. We soft threshold the singular values, and that's what the matrix soft thresholding operator returns. That's pretty challenging to do at scale. Right? So here's an example of a proximal operator that's pretty sophisticated. So just keep in mind when we talk about the number of iterations of, for example, this algorithm, it's still 1 over epsilon, but each iterate on the order of 1 over epsilon to get an epsilon accurate solution, but each iteration is very expensive. OK, are there any questions about that stuff? So sometimes you'll hear people call proximal gradient descent different names. The two names that you might hear it called other than proximal gradient descent are composite gradient descent or generalized gradient descent. So two things that people often refer to it as. Composite is, the name for that is kind of obvious. It's because we try to minimize composite functions, smooth plus non-smooth. Generalized refers to something else, which is that through several special cases of proximal gradient descent, we can get back kind of known algorithms. Right? So it's a more general version of, for example, any of these algorithms. When you take h equals 0, I claim that we just get back gradient descent. See, I didn't write that out in the next slide. Why is that true with gradient descent? So remember the proximal operator associated with h at some level t, it's just defined as the argmin over all z of 1 over 2t x minus z squared plus h of z. It's the point that's closest, that minimizes this criterion. So what happens when h equals 0? What is this operator? Sorry? Yeah, right? The answer is just x. So it is a quadratic, that's right. But what's the point z that's closest to x? It's just x. So when that's true, the proximal operator at any level t, it doesn't matter, is just the identity mapping. So what are the proximal gradient descent steps? Remember, I just take x plus, which is equal to the prox of x minus t times the grad of g, But this is just the same thing as x minus t grad g, right? Which is just gradient descent on g. So it's when h is 0, when all we have is a smooth part, we're not doing anything different than gradient descent. That's comforting. When h is the indicator of a certain set, we get back an algorithm called projected gradient descent. So we didn't talk about how to do gradient descent with constraints. Proximal gradient descent actually provides a way to do that. When g is 0, we get something called the proximal minimization algorithm. Okay, something we haven't learned yet. We learned the subgradient method for minimizing kind of generic convex but non-smooth functions. This is an alternative to that. All of these algorithms we know have a convergence rate of 1 over epsilon, and they converge, right, under this appropriate step size choice. That's what we know by virtue of knowing the convergence behavior for proximal gradient. These are all special cases. So had we only learned proximal gradient and nothing else, we'd already have been able to say everything that we did about gradient descent, projected gradient descent, which is nice, and this other thing called proximal minimization algorithm. So I'm just going to go through these very quickly. We're already behind. But projected gradient descent is something that is quite useful, right? If you have a constraint set and you're trying to minimize a smooth function subject to constraints, and then we can use what we call projected gradient descent, provided that we know how to project onto the constraint set. So what's the proximal operator here, right? If I give you h being an indicator function of some set C, which means that it's 0 whenever its argument lies in C and infinity otherwise, then minimizing g of x plus the indicator of x being in C, it's the same thing as minimizing g of x subject to x being in C. Right, we saw that earlier, just a different way of writing the constrained problem. We can rewrite a constrained problem as an unconstrained one where we add in the constraint as an indicator function. And the proximal operator for this particular choice of h, you'll see it's just the projection operator onto C. For the same reason, right? If I ask you to minimize this L2 squared distance between x and z divided by 2t plus the indicator function of z being in C, then all I'm going to do is I'm going to try to find the point in C that's closest to x, right? For the same reason. This is going to be infinity outside of C, and it's going to be 0 inside of C. So it's really just the projection operator onto C, something that we've seen before. Okay, so in that case, the proximal gradient descent algorithm, right, it repeatedly takes a gradient step with respect to g, and then it applies the prox operator, which is just a projection onto C. So we get back an algorithm called projected gradient descent, which is something that's pretty natural, which says take a gradient step with respect to the loss, the criterion g, and then because we have to be in the constraint set, project yourself back onto the constraint set C. Find the point in C that's closest to where that gradient step took you. It's not obvious that this method converges, right? If we learn gradient descent, we may have to think about how to reprove it for something like this. But since we already know proximal gradient descent converges, it's a nice kind of general framework. We know that this converges and also has the right convergence rate. It converges just as quickly as gradient descent. This projection operator, by the way, this could, again, it could be cheap or expensive. So the per iteration complexity could be different. For a lot of sets, projections are possible and cheap, but for others, they're not. Right, so here's the picture. Suppose our constraint set looked like this. These are the contours of our criterion. We would take a step towards along the gradient of the criterion function, and then we'd have to project ourselves back onto the constraint set for our next iterate. It's projected gradient descent. Okay, and I don't know if we actually mentioned this, but projected subgradient method works too, just so that you know, just so that you're aware of that. The other one that is a special case is called the proximal minimization algorithm. This is not really one that people study that much anymore. This used to be more popular, I think, kind of in some of the more classic literature of optimization. But it's an algorithm for minimizing, again, a convex but not necessarily differentiable function. This is the special case when we take g equals 0. So all we have is minimize h of x for some particular non-differentiable but convex function h. And we know how to do this with subgradient descent, right? But we can also do it in this framework by just considering the special case when g is 0. What it reduces to is actually just repeatedly applying the prox, right? Because there is no gradient step. There's no g. So you just repeatedly apply the prox over and over again to minimize h. This, we know, has convergence rate 1 over epsilon. So in principle, it's actually a lot faster than subgradient method. Subgradient method had convergence rate 1 over epsilon squared. So these have very different convergence behaviors. This is actually not studied very much anymore because it's not very practical. We have to know the prox operator in order to do this. So really only in special cases do we know the prox operator. We've already talked about that so far. If you just give me a generic convex function that's not necessarily smooth, I will be likely able to compute its subgradients. That's pretty generic. But being able to compute its prox operator is a lot harder. So people don't really use this much anymore, although in principle, if we could, it would be faster than the subgradient method. Any questions about those special cases? Yes?
What are some tools that you can use to find the projection on a set?
So I had a slide on having you calculate how to calculate projections. Maybe I'll put it back in the lecture notes and then you can take a look at it. We'll put some exercises in the homework too. Essentially, the answer is that there is for a class of different sets, projections you can just look up. Like projections onto certain types of polyhedra, linear subspaces, certain types of norm balls. Those things are well understood and you can just kind of look up. Other projections, you can treat them as a convex optimization problem and try to derive the optimality conditions through subgradient optimality like we've done before, and then write down the projection operator. That will work. But the trouble with projections is that you can move from one example to another, and it can get a lot harder, and you may be stuck driving the projection operator. So that's why I'll put the lecture slide back in. We'll put some exercises on the homework. You can get a feel for kind of what is possible and what's not. But just as an example, if I had an arbitrary polyhedron, the set of all x such that ax is less than or equal to b, for just an arbitrary matrix A, then this is actually very hard to project onto in general. So projecting onto this is a quadratic program, right? Finding the point x that's closest to some other point, some other fixed point, say C, is a quadratic program. There's not a closed form for that. It's actually very hard to do in general. But for certain special cases of A, we can do this efficiently. So that's why projections can be deceiving in a sense. Good question. So this is one thing that you inevitably face in practice while you're doing the proximal, while you look at proximal gradient descent algorithms, which is that you come to a problem you want to solve. You recognize it as smooth plus non-smooth, and you think, I want to apply proximal gradient descent. And you go and you can't evaluate the prox function. Right? It's something that's not one of the cases that you've seen in class, and you try to write down the subgradient optimality, and it just looks like it's not analytically tractable. You can't find a closed form. So people inevitably do is they actually just treat this as a separate minimization problem. Right? Within the step where you're supposed to evaluate the prox, they'll run something else to try to evaluate this. Some other optimization algorithm we've learned to try to evaluate the prox, because this is itself a minimization problem. And they just plug that in, right? They iterate a bunch of times, get an approximate solution, so evaluate the proximal operator approximately, and then move on with their algorithm to the next iteration, and then do it again. So just treating this, like I said, as another minimization problem and applying another optimization algorithm to it. That's something that people do in practice. It's not uncommon. But in general, if we do this, all bets are off in terms of the convergence rate. What we know is that if we evaluate the prox exactly, then we get a convergence rate of 1 over epsilon. If we evaluate it approximately, then you can see that we're not really taking the right update. Right? We may be actually taking an update that's, in some sense, it's noisy. We should have been taking the prox of the gradient step with respect to g, but we're taking something that's kind of off from that. If those errors accumulate, if there's kind of a big enough error in each time you approximately evaluate the prox operator, then the algorithm might not converge at all if they kind of accumulate over the iterations of the proximal gradient descent method. So I guess the take-home message is that in general, if you're going to approximately minimize the prox operator, you should be very careful in assuming that would converge. However, in practice, it tends to work out if you evaluate this proximal operator kind of to high precision. So you run whatever optimization algorithm you want to a high level of accuracy. And there's emerging theory that's saying that if this is done appropriately, then it still converges. So here's a very recent paper that studies this. It basically puts a condition on how much error you can incur over each iteration of when you approximately minimize this inner minimization problem that's defined by the proximal operator. Okay. So the last thing I want to talk about when it came to this proximal gradient unit was acceleration. In past years, I've given entire lectures about acceleration. I mean, I think one could give more than one lecture on acceleration. But I think what it comes down to is that it's something that's very useful that you should see and then look back and use when you feel like it would be useful. Yeah?
Yeah, but why is it more sensitive than this gradient descent? Why is this more sensitive than this gradient descent?
I mean, if I get an inexact gradient? Yeah, in a sense, it's not more sensitive, but the proximal operator could be very flat around its solution. So you could, if the proximal operator is very flat around its solution, right? What controls the curvature of the proximal operator? It's really the strongly convex part, which is this part. And this is strongly convex with parameter 1 over t. So if you're taking large step sizes, then this doesn't have very much curvature. So you could try to approximately minimize this, and you could say that, suppose you exit when you think you're close to the optimal criterion value. The actual solution that you're trying to find, you could be far off from with the proximal operator. So I don't think it's much more sensitive in terms of the amount of error you can tolerate than gradient descent. It's just more likely that you'll encounter noisy updates here than in gradient descent. And this paper has conditions that say something like, suppose you encounter error delta k at iteration k when you're trying to minimize the prox. If delta k is summable, if I add up delta k over all iterations of the algorithm and it's finite, then I'll get a convergent solution. So somehow you have to encounter less and less error as you go along. You want to make the whatever algorithm you're running to find the approximate solution here, you want to make it more and more accurate across steps of the algorithm. But it's a good question. I mean, I think there's emerging theory for all of this, right? For what happens when the gradient itself is noisy, the proximal operator is noisy, and we have results that tell us what to do in that situation. It's just never clear in practice whether you're in a situation where those are met. Okay, so I'm just going to tell you what acceleration is, basically, without going into the details. I don't think the proof is super insightful as to why acceleration helps so much. We've done that in previous years, but I don't think it's, the students have really gotten much out of the proof. But it's a very interesting idea, and it's due essentially to one person, to Yuri Nesterov, who's somewhat of a very influential figure in optimization, especially in the last 15 years or so. So a long time ago, Nesterov had this paper on acceleration for smooth functions. That's the kind of first paper you'll see about this in 1983. I think that none of this really got picked up until people started looking at proximal methods. And then it really took off. So there's a sequence of other papers, right? I've written down 4 papers here by Nesterov, and then a paper by Beck and Tabul, who took this idea and made it simpler in some sense. And applied it to proximal algorithms, proximal gradient descent algorithms. And all throughout is the idea that if we use more than just the last iterate, if we try to use more information than just where we've been in the last step, and we carry some kind of momentum through across iterations, then we can actually accelerate the convergence rate of, say, gradient descent or proximal gradient descent from 1 over epsilon to 1 over the square root of epsilon. And from something we saw earlier, that's actually the optimal convergence rate for first-order methods. So in terms of rates, we can't do better than that. So this is achieving the optimal rate for first-order methods. So what's accelerated proximal gradient descent? It looks like proximal gradient descent, except for we changed the argument that we pass to the prox function. And we changed the step at which we make the gradient update with respect to g. So we keep track of essentially the iterates x, but before we pass, right, if we were doing regular proximal gradient descent, we would just pass xk minus 1 here minus the step size times the gradient of g at xk minus 1 to the prox operator and move on. In accelerated proximal gradient method, we do something different, which is that we take the last iterate and we add something to it. And this is what we call a momentum term. And you can see that if we are moving from xk minus 2 to xk minus 1, then this term kind of continues to push us in that direction. So we're at xk minus 1, and instead of just evaluating the prox at xk minus 1, we allow some of the history, the direction that we are going to get there, to push us a little bit further. And then we define that to be v. This choice of constant, actually, it turns out to be quite important for the convergence of the algorithm. So this is taken as a fixed constant, k minus 2 over k plus 1, not something that you have to tune or that you should tune. Although there are other convergent strategies, this one is provably convergent. And what we can see is that when k is 1, right, at the first step, we're just doing a proximal gradient update. After that, we're carrying momentum from previous iterations. And what do these weights look like across iterations? So do they get bigger or smaller as k increases? So when k is 1, right, this thing is, oh, maybe I meant to say k is 2. But in any case, it doesn't. When k is 2 here, I guess, we're going to get the usual proximal gradient update. And as k gets larger, do these weights get larger or smaller? What do they approach as k gets bigger and bigger? That ratio, k minus 2 over k plus 1. Just approaches 1, right? As k gets larger and larger, this thing approaches 1. So here's what the weights look like. The momentum weights gets larger and larger as the iterations of the algorithm proceed. So what does that mean about the momentum? When are we applying more momentum? We're applying more momentum later on in the steps of the algorithm. Right? So at the start, we're letting the iterate that we're visiting mostly dictate where we're going. As the algorithm proceeds, we're allowing the history to push us more and more in the direction that we were going. So why is that helpful? There are kind of a few proofs of why this gives you a faster convergence rate. I don't know how insightful they are. And honestly, this is somewhat of a cliched statement, but everyone says this. Intuition for why this particular scheme works is really lacking in terms of acceleration. Something that we understand mathematically, but not intuitively. Here is an intuitive explanation that I think is pretty good, but it doesn't tell the whole story. If you're at a late step in the proximal gradient descent algorithm, for example, then the gradient's going to be small because you're going to be close to the optimum, right? So you're not going to be really moving very much because you're trying to move in the direction of the negative gradient. It's pretty small. So the progress of the algorithm is going to be pretty slow close to optimality, just by virtue of the fact that you're close to the optimum. At this point, acceleration says that if you're in a good neighborhood of the solution and you've been traveling there, it's going to continue to push you in that direction. And it pushes you more at the later steps of the algorithm, which is exactly when the gradient is small. Right? So if you imagine a picture like this, where these are the contours of the function you're trying to minimize, then as you get closer and closer to optimality, say with proximal gradient, the step sizes get smaller and smaller. Right? even if the effective step sizes get smaller and smaller, even if the step size itself was fixed, because we multiply by the gradient of the loss function. So effectively, because the gradient's getting closer and closer to 0, the steps are being contracted. What acceleration does is that it says if you're going in the right direction, right, then instead of just taking the next iterate to be, where you are minus the gradient of the loss function, you're going to add something which is along the direction of where you've been going. Right, so you're going to add some amount. If this was xk minus 2 and that was xk minus 1, then you're going to be adding this direction to the next iterate before you apply the proximal operator. So it's accelerating you in the kind of direction that you've seen over the history of iterates. And that acceleration gets larger and larger because these weights get closer and closer to 1 as you get farther down steps of the algorithm. So if these weights were tuned in properly, then we would somehow be accelerating ourselves maybe in at the wrong time in terms of the optimization procedure. We might be pushing ourselves kind of farther away from optimality. But this particular tuning of weights, this one here, it kind of pushes us in the right direction just at the right time. So computationally, this is really not much more expensive, right? Instead of passing this to the prox operator, generically, we're just changing the argument. Yeah?
This kind of acceleration won't work for
Stochastic
stochastic
methods? No, we don't really. Oh, stochastic gradient descent, you're saying. That's an interesting question. I'm not sure. I'm not actually aware of much work that combines those two ideas. You're saying because the gradients directions are so noisy already? Could be, yeah. But so what people do in stochastic methods, which we didn't mention, but we may come back to, is people often do mini-batch methods, which means that instead of just picking one function to minimize and taking the gradient with respect to that function, you take like a subset of the full set of functions, and it's called a mini-batch, and you evaluate the gradient over those. So that ends up being much less noisy. So maybe mini-batch combined with acceleration could work. Although I'm not really aware of people that, I mean, I'm sure it's out there. I'm just not aware of work that's combined it. Okay. Yeah.
So, if you don't have proximal step, this would have been just another scalar you multiply for every with the time step with these.
Ah, I see. No, so that's not quite true. It's a question I get asked every year because I think it seems like it. But when h is 0, like you said, pretend like there's no proximal part, then I'm just doing accelerated gradient descent. So remember, this prox goes away, and I'm really just taking the update to be v minus tk grad of g at v. Let me actually not answer that question and see if you guys can think about it and figure it out. I'll just draw the picture and you can think about it. Just because it ends up invariably taking a while to explain. And it's something I think you can think about and figure out. If not, we can revisit it either in a later class or in office hours. But I'll rephrase the question, which was that let's suppose my updates were just as follows. xk were equal to v minus tk grad g of v, where v is equal to xk minus 1 plus k minus 2 over k plus 1 times xk minus 1 minus xk minus 2. So this would be accelerated gradient descent, which is a special case when we take h equals 0. So the question was, isn't this just the same as taking a longer step size, effectively, right? And it's not the same. It's not the same because you're evaluating the gradient at a different spot. And you can draw yourself a picture to kind of convince yourself that's true. Mark down xk minus 2, xk minus 1, and xk here. You'll see that you're actually evaluating the gradient at a different spot than had you just taken a longer step size. So it's a fair question, but it's not quite the same. Which is good because we know that gradient descent converges at a rate 1 over epsilon, and this converges at a much faster rate, so this better be doing something different. Okay, all good questions. So here's just an example of how acceleration can really help. We've solved this problem now in 3 ways. So the first thing I did was take subgradient method, I showed you this in the subgradient lecture. This was something like a lasso penalized problem, just a L1 penalized regression. We could apply subgradient method to that. It has a convergence rate 1 over epsilon squared. We know that, and the subgradient steps are fairly simple. Last time we looked at an algorithm called ISTA, which is the iterative soft thresholding algorithm. It's just proximal gradient descent applied to that problem. So each iteration is soft thresholding. That was the red curve. Achieves a convergence rate of 1 over epsilon, so which is a lot faster than 1 over epsilon squared. Now I'm applying acceleration. I'm applying Nesterov acceleration to proximal gradient descent. People call that FISTA, the fast iterative soft thresholding algorithm, although those names I think are kind of silly, but you'll at least see them written down a bunch of places. This has convergence rate 1 over the square root of epsilon. So again, these are 3 different regimes of convergence. You can see that they really make a big difference in practice. One thing that you might notice if you looked carefully, and if we stretched out this x scale here, so all you saw was this blue curve, say from iterations 1 to 100 or something like that, you would see that actually the blue curve is not monotone decreasing. So we get these things called Nesterov ripples, which is, I guess, an affectionate term because of the fact that Nesterov invented acceleration. You'll see that actually oftentimes when we apply acceleration, this is what the criterion looks like across iterations. And this is just, I'm trying to emphasize the fact that it's not a descent method. So acceleration actually does not guarantee that we descend the criterion at every iteration, unlike proximal gradient descent, which we know does. So that you shouldn't be surprised if you apply acceleration, you see something like this. This is actually not unexpected. And on your homework, you're going to be implementing acceleration, I think, for a problem something like this, and you're going to try to be recreating a picture like this. OK, convergence analysis is basically what I said. Under the same assumptions, it gets a rate of 1 over the square root of epsilon, or the difference between the achieved criterion and the optimal criterion after k steps is something like 1 over k squared. The proof for this, I reference a paper in all of Nesterov's papers at the end. You can take a look at the proof. It's pretty different from our proof for proximal gradient because of the fact that this acceleration, I think, is actually kind of an interesting creation. The proof is a bit subtle in that way. Backtracking is possible with acceleration. The backtracking strategy is really quite similar to what we did in proximal gradient. So here's the criterion that we use to exit the backtracking strategy. This slide you'll get to know and love when you go to the homework, because we're asking you to do acceleration with backtracking, so that you'll pay attention to. One of the differences between what we have to do here and in other strategies is that if we took a certain step size at step k, then the step can only be smaller than that at step k plus 1. We actually force ourselves to choose smaller and smaller steps across iterations. That's not always true with backtracking. With backtracking for gradient descent, say, we just chose some initial level that will always start from like 1. Here, to make it work, and this comes from figuring out where one can apply backtracking in the proof, we have to make sure that the step sizes decrease across iterations. So it may be less effective in some sense than backtracking with other methods. Because if we ever took a small step size at one iteration, we've kind of forced ourselves to take step sizes that are at least that small in all future iterations. Lastly, I wanted to talk about this idea: is acceleration always useful? So it seems like it's such a good idea that you might want to use it for every problem. And there may be no reason to use just proximal gradient on its own without acceleration. But you'll still see a lot of implementations of fast algorithms that are not accelerated. And that's for pretty good reason. It's generally a very effective speed-up tool, but it's not always the thing to turn to. And here are a few things to think about when we think about applying acceleration. First of all, the gain you get from acceleration is often diminished when you're solving many optimization problems in sequence, and we're using what's called warm starts. So in many of these problems we've talked about, there's some penalty parameter. Like with the lasso, there's the penalty parameter lambda. With matrix completion, there's a penalty parameter. Whenever we have like a loss plus regularizer, there's always a penalty parameter. And what we often do in practice, and again, you'll actually implement this on your homework, is we solve a sequence of these problems at the largest value of the regularization parameter, say, or at one end where convergence is easy. And then when we finish that particular problem, we move on to the next one, and we initialize our optimization algorithm with the solution of the previous problem. Right? So this is called warm starting our optimization algorithm. So it's just written down here. Solve for lambda 1 to the biggest value, initialize it arbitrarily, in some sense, record the solution at that lambda value. I'm calling that x hat of lambda 1, just to go back to the hat notation we often use in statistics, say. Then when we're solving for another value of lambda, say lambda j, we're going to initialize it at the recorded solution for the previous value of lambda. And when we do this, the number of iterations required to converge later on in the warm starting sequence is often much less than if we just started at that value of lambda arbitrarily. Why is that? It's because we're already close to the solution when we're starting off. If we believe that the solution is continuous as a function of the regularization parameter lambda, which in most cases it is, then this warm starting is already putting us close to the solution rather than starting at 0. So in a sense, we're already kind of in a good regime. And acceleration in this context often doesn't do much than just running something like proximal gradient. This warm starting often supersedes the need for acceleration. It doesn't hurt in general in this situation, but it's often not worth the trouble. So people, when they solve these problems with warm starts, they sometimes don't apply acceleration. Sometimes acceleration and even backtracking can be harmful, actually. Sometimes they can actually make your life harder when you're implementing an optimization algorithm. And the matrix completion problem is a good example of that. The details maybe aren't worth going through super carefully, but take a look at this if you're interested in matrix completion. If that's something that you're interested in for your project or just in general, you can take a look at the slide more carefully. Essentially, when we move from, let's say, unaccelerated proximal gradient to accelerated proximal gradient, what we're doing is that we're evaluating the prox at a different argument. Right? So the Proxima operator we know here is take an SVD and apply soft thresholding to the singular values. When we accelerate it, we take an SVD of something else. We're actually like adding something to the object that we originally would have taken the SVD on. The original object that we would have taken the SVD on, in the context of matrix completion, is a sum of two matrices. It's something that's sparse plus something that's low rank. And taking the SVD of a combination of sparse and low rank matrices, we actually have tricks for how to do quickly. That's something that people I've studied in another context, let's say. And so that SVD can be done in an efficient manner. The first term was the projection of y onto the observed set. That's sparse if the observed set is quite small. The second part is low rank by construction. We're constructing the estimates to have low rank. When we apply acceleration, we actually change this part b. This is the iterate at which we're evaluating the gradient. We change it to something else, which is v. If you look back at the form of v, you'd see it's no longer at low rank. And actually, its rank can change because it's the sum of things from previous iterations. So it kind of ruins this nice structure, and it means that the SVD that we actually have to take to get the Proximal operator can be a lot slower. So people almost never apply acceleration in matrix completion if they're using something like proximal gradient. All right, so the conclusion is that it's a useful tool, but not something that, say, you should always expect to give better performance. All right, that was about it for the proximal gradient and acceleration lecture. There's a ton of references on this stuff. I put some at the end. It's a very popular topic for current research. So I guess it's somewhat of an exciting time in terms of this topic. Any questions about proximal gradient and acceleration before I move on to the numerical linear algebra stuff? No? OK, let's take a couple-minute break, and then we'll do our numerical linear algebra lecture. Short break, but I want to give you some good training with numerical linear algebra. This is the last lecture we have in terms of our algorithms units for first-order methods. And the first-order methods, just to put it in context, that's some pretty classic material. So gradient descent, subgradient descent, even proximal gradient descent, that's some pretty classic material. It's been studied for a long time. Acceleration, which we only very briefly touched upon, is very recent. So it's kind of like, in a sense, a regeneration or rebirth of all the exciting ideas in first-order methods. And people, like I said, are studying that currently. You'll see papers at NIPS or other conferences that try to improve on acceleration or understand it better, even each year. So we went from classic stuff all the way up to more recent stuff. Before we move on to our next unit, I wanted to talk about some of the kind of computational underpinnings, or some of the stuff you need to understand in order to figure out how computationally expensive some of these methods are. And this is going to be especially relevant when we think about first-order methods compared to second-order methods. In past years, I've just kind of assumed that people would be comfortable with how expensive a matrix multiplication would be, or a matrix solve would be, et cetera. And I got some people who were really comfortable with it and people who were pretty confused. So this year we're going to try to do a primer on numerical linear algebra so that we kind of get ourselves on the same page in terms of how expensive are some of these fundamental operations. If nothing else, you should walk away from this lecture when we come into second-order methods, which are coming up in our next algorithms unit, with the idea that solving a linear system is generically more expensive than multiplying a matrix by a vector, say, or by taking an inner product of two vectors. And that means that doing something like a second-order method is more expensive in terms of iteration complexity, in terms of the complexity of each iteration, than something like a first-order method. And we'll see the details of that in this lecture, and hopefully you can keep it in mind as we kind of talk about linear systems throughout. So here's what we're going to go through. Some of this may be review for people. I think a lot of people may have had this in other courses. So this might be new to some other people. So we'll just talk about the complexity of some basic operations. How expensive is it to solve linear systems? And then what do we get from things like matrix factorizations and so forth when we talk about the computational cost of solving linear systems? Okay, and in case it's not clear, solving linear systems is in a sense at the heart of a lot of these optimization methods. So we haven't really talked about that so far with first-order methods because all that's been is computing a gradient or taking like inner products of vectors. But when we talk about second-order methods, which really the heart of those is a linear system solve. So what is one way to measure the complexity of basic operations? We use what's called a flop. It stands for a floating point operation. And a flop counts one of the following things: an addition, a subtraction, a multiplication, or a division of two floating point numbers. This just means that we're not storing them as integers in memory. We're thinking about storing them as floating point, with floating point precision. So in truth, a division is actually more expensive than these three operations, but we still count it as a flop. Okay, so it serves as a basic unit of computation. How many flops does an algorithm use is a model for how expensive it would be to run. This is a rough measure of how expensive it is, and we don't think about exact flop counts because those actually aren't very informative. There are a lot of other things that affect the practical runtime of an algorithm other than flops. It's not a perfect measure by any means, but we're interested in rough flop counts because it roughly reflects on kind of standard computer architecture how expensive it would be to perform a given sequence of operations. So let's just go through some basic operations. Hopefully all this you can internalize if it's not already internalized. How expensive is it to add together two vectors that are each of length n? How many flops does that cost? So we're talking about element-wise addition of two vectors. It's just n flops, right? Because I'm just adding up each component. So I'm doing n additions, that's it. Scalar multiplication, so a scalar times a vector, also costs n flops. I'm just doing n multiplications. An inner product between two vectors takes on the order of n flops, but it's closer to 2n, right? Because I'm having to multiply every component of A by every component of B, so n multiplications, and then add them all up, which is actually n minus 1 additions, but we'll just count it as n. So we're going to say it's 2n flops. Okay? Flops don't tell the whole story. They're not a perfect measure by any means, like I said, of the computational complexity of some sequence of operations. For example, if I want to set every element of A to 1, so if I ran something, some code, maybe my code looks something like this in C notation. That would be 0 flops. Doesn't cost me any flops. I'm not doing any addition, subtraction, multiplication, or division. Okay, we might think it actually costs something more like n operations, but in terms of the flop count, it's 0. Okay, So that's just an example of how I said flops don't tell the whole story. But we're going to keep track of them anyways because in many cases that's what we care about. Okay, moving on to some more sophisticated operations. How about matrix vector operations? In particular, matrix vector product. So if I have an m by n matrix and a n-dimensional vector, what is the product of A times B cost? This is A, and say this is B, m by n. Well, we know that a single inner product costs about 2 times the length that inner product flops. Right? So if I just take the inner product of one row of A with B, that costs 2n flops. To do the matrix multiplication, I actually need to do m of those, right? I need to take the inner product of every row of A with B, so it's 2mn flops. If A is sparse, then this is a very nice property of sparse matrices. You convince yourself it takes something like 2s flops, where s is the number of non-zero elements in A. Right? That you can think of that. You can remember that by thinking about the general case, where it takes 2mn flops. M times n is generically the number of entries in A if A was dense. When A is sparse, we replace that m times n with s. Right? If you think about why that's true, it's because for every non-zero element in A, if we were storing those in some kind of clever way, and we can just iterate over those, but actually doesn't matter because flops don't count anything but additions, subtractions, multiplications, and divisions, you only have to multiply the non-zero elements of A by the corresponding elements of B and add those up. And so how many non-zero elements are there total? There's just s. And so between a multiplication and division, that's just 2 operations for s elements makes 2s flops. When A is banded, it takes 2 times n times k flops. So in that case, A looks, here I said A was square, just for simplicity. A is banded means that it only has non-zero elements in some bandwidth around its diagonal, and there's k elements that are non-zero in this band, and these are all zeros. This is a k-banded matrix A. This only costs 2 times n times k flops. Right? You can think about for the same reason as the s-sparse one does, for example. If we could factor A as a sum of rank 1 matrices, and there's r of them, that means that A has rank r, then multiplying A by the vector B costs 2 times r plus m plus n flops. You can see this in a couple of ways. First way you can see this is by looking at it as follows. Right? How expensive is it to multiply V by, to do this inner product, Vi transpose B, it's 2n flops. How expensive is it to do the element-wise product of Ui times this scalar? That's just something like m flops, right, because this is length m. And we have to do r of these, so that it ends up being total 2r times m plus n flops. So if A is rank r, then actually matrix multiplication is a lot cheaper if r is small. Right? This 2 times r times the sum of m plus n is going to be a lot smaller than 2 times n if r is a lot smaller than m or n. So low rank matrices we can multiply quickly if we have factored them. Right? Another way of saying that A is the sum of ui vi transpose is saying that A is equal to u times v transpose for some matrices u and v, where these have these u is m by r and v is r by n. For permutation matrix, how expensive is that? Permutation matrix actually costs 0 flops because, again, we're only counting flops. So it's an imperfect measure of how expensive this operation is. Permutation matrix only has one 1 in any given row. So this is an example of a permutation matrix. Something like this. And if we multiply this by a vector b, then we're just rearranging, we're permuting the elements of b, but it costs 0 flops. because we're not actually doing anything. Thank you. Okay. Any questions? It's just kind of basic operations we're studying at this point. Matrix-matrix product costs something like 2 MNP flops, where we've changed B from being an n vector to an n by p matrix. Again, you can, if you remember the matrix vector product, you can see this one because we're just doing a matrix vector product for every column of the matrix B now. That's how we get the product A times B, or B is a matrix. So we're just multiplying this by p, the number of columns of B. And for an S sparse A, it costs 2 times S times P flops. Again, for the same reason, we're doing a sparse matrix multiplication for every column of B. It's less if B is also sparse. So theme alert, sparse matrices, we can do things more cheaply. Banded matrices, we can do things more cheaply. Permutation matrices, we can do things for free according to this measure of complexity. So these are the things that we want to look out for if we're able to structure things accordingly. Matrix-matrix vector product. This is one that when you're learning to program, you maybe did the wrong way and you didn't realize that it was more expensive. How expensive is it to multiply A by B by C? Well, it's either not too bad or it's pretty expensive depending on how you do it, right? So if you multiply A by B times C versus A times B times C, then those have different computational complexities in terms of their flop counts. Right, in one case, we're doing a matrix-matrix multiplication, and then a matrix vector calculation. In the other, we're doing a matrix vector calculation and a matrix vector calculation. So they have pretty drastically different flop counts. Here's the meat of what we're going to study, solving linear systems. So how expensive is it to solve a given linear system, say AX equals B, where at this point A is square, and it's invertible as an inverse. So how expensive is it to compute x equals A inverse times B? In general, what you should remember is that costs on the order of n cubed flops. So if A is n by n and it's dense, solving a linear system is n cubed flops. Let's go back to these things. If A is square, then matrix multiplication of A by B takes on the order of n squared flops. Very different, right? N cubed versus n squared. And an inner product between two vectors that are both of length n cost n flops. So vector-vector multiplication is n flops. Matrix vector calculation is n squared flops. And a linear system solve is n cubed flops. So those are all very different in terms of their complexities, especially when n is large. That can make a huge difference. But there are some matrices that we can actually, for which we can solve linear systems in a much more efficient manner. And here are some examples of them. If A was diagonal, then solving AX equals B only cost n flops, right? Because in that case, I only have to, suppose the diagonal elements of A were A1 through AN, which means that, right, A was all zeros except for on the diagonal it had these numbers. Then solving AX equals B just requires dividing every component of B by the corresponding component of the diagonal. That's just n flops. For a lower triangular A, we do something called back substitution. So lower triangular matrices look like the following. They have only non-zero elements on the diagonal and below. So these are all non-zero, and these are all 0. How do we solve a lower triangular system in an efficient manner? We do something that's called forward substitution. So if we look at the first, suppose we want to figure out the first element of x, then we realize that's only specified by a linear system in x1. Right? This tells us that a11 times x1 equals b1, because every other element in the first row of A is 0. So it tells us that x1 is equal to b1 over a11. And now if we move to the second row, there's only 2 non-zero elements in the product of that row with x. And so it's only a linear system in x1 and x2. So we get a21 x1 plus a22 x2 equals b2. And because we already know what x1 is, we can just substitute that in and solve for x2. And while this cost 1 flops, this is going to cost something like on the order of 2 flops. Okay, and as we go forward, solving for the kth row is going to take on the order of k flops. The number of flops in total is on the order of n squared. The sum of I going from 1 through n is like on the order of n squared. Okay, so it's going to cost about n squared flops to solve a triangular system, which again, very different from n cubed flops for a generic system. You have an upper triangular matrix, so if instead of having non-zeros below the diagonal, if I had non-zeros on the diagonal and above, then it's analogous strategy. It's called back substitution. We just solve for xn first, and it also costs n squared flops. For a sparse A, there's not a generic way to solve a sparse linear system in a, I'd say, practically sound, efficient manner. It depends on the sparsity pattern. So there's not a generic rule like there is for, say, lower triangular matrices, or for band matrices. But it often costs a lot less than n cubed flops. In the worst case, it can still be n cubed, even with a fairly sparse matrix, because it actually matters the structure of that sparsity that matters a lot in terms of the flop count and the resulting algorithms. That gets to be fairly complicated. We're not going to talk about sparse algorithms for algorithms for sparse linear systems. There's entire books about that, but the takeaway point is that it can be done often a lot more cheaply than for a dense system. It can often be done even in linear time if the amount of sparsity S is linear on a linear order with n. But exact worst case flop counts are difficult. For more structured matrices, like band matrices, which are obviously sparse, we can get worst case guarantees that are very good. So if A is k-banded, which is this picture, remember it was banded with bandwidth k, then it costs n k squared flops to solve that linear system Ax equals b. K is usually pretty small, so that's just usually considered to be linear in n. So banded linear systems we can solve very efficiently. Orthogonal matrices we can also solve quickly because their inverse is just their transpose, right? So if you have an orthogonal matrix, again, you should recognize that, and you would perform a matrix multiplication rather than a linear system solve. And that's just on the order of n squared again, for the same reasons we had before. And just to tell you, again, permutation matrices apparently are free according to our measure, but we may convince ourselves that it's more like n operations with a more generic measure of computational complexity. But for permutation matrix, it's a special type of orthogonal matrix where there's only one 1 in each row, and its inverse is just its transpose, something that you can check to convince yourself just by going through some examples. So solving that linear system, again, costs 0 flops. I'm just going to continue blazing ahead unless there are questions, so make sure you guys interrupt me if you're unsure about something. I'm not sure how many people for this who've seen this kind of stuff before, this is review or whether this is actually new. So if you're having questions, make sure you stop me. I'm going to keep a pretty fast pace. Okay, matrix factorizations are, at least in the context of what we call direct methods, these are the ways that we solve linear systems in general. You might have learned in a previous course, potentially even high school, people learn about Gaussian elimination. It's a way to solve linear systems. It can be much more useful in general to factorize a method and perform what we call a factor solve technique than Gaussian elimination. And there are various reasons for that. The biggest reason is that by factorizing, we often can solve many linear systems in A where the right-hand side changes in a way that's much cheaper than having to perform separate linear system solves. So by factorizing a matrix A, we mean that we're going to express it as a product of simpler matrices, k of them. So A we're going to express as a product of A1 through AK. And usually these A's are simpler, so they're orthogonal, triangular, diagonal, or permutation matrices. Those are the kind of ones that we want to end up with. We already saw why. It's because solving linear systems in those matrices is a lot cheaper than solving linear system in a dense matrix. Usually we only factor as a product of 2 or 3 matrices, so usually k is small, like 2 or 3. And in order to solve the linear system ax equals b, we just solve these k linear systems individually, right? Inverting this matrix, if all these factors are invertible, I just invert each one and reverse the order. So I first solve a1 times x equals b, then I solve the system a2 times x equals whatever the answer was to that, etc. Okay? So computing the factorization is often expensive. So just computing this is often the same cost as solving a linear system. So it's n cubed flops. So in that sense, we're not doing any better. Once we have this factorization, because these are special matrices, applying this factorization in this manner to solve a linear system only costs n squared flops usually. That's because, like I said, each one of these linear systems can be done efficiently because these matrices are structured. So getting the factorization in the first place is n squared flops. Once we have the factorization, we get the answer in n cubed flops to get the factorization in the first place. Once we have it, we take n squared flops to get the solution. So that means that if we wanted to do this, suppose we wanted to solve the problem ax equals b and ax equals b prime and so on and so forth, then we would just factor a once, which costs n on the order of n cubed flops, and then we would use it to solve ax equals b prime, etc. And each of these steps would then only take n squared computations. So if we had a lot of them, then this would be saving us a lot of computation time. Was there a question up there that I skipped over?
Are we assuming a square method?
So as I've written it, yes, because I'm writing it as having an inverse, but factorization methods apply to rectangular matrices as well. We'll see that. We'll talk about the QR factorization, which doesn't need a to b square. OK. Is that clear? Any questions about that? Another reason that we like to use factorization methods is because often if a undergoes a simple change, like if I told you to solve the problem ax equals b, and I asked you to solve a prime x equals b prime, where a prime was just a little bit different than a, then if you applied, say, Gaussian elimination or some generic technique, it would be about the same cost. But with a factorization method, we can often get the factorization for a prime from that we got for a with a very simple update. If the difference between a prime and a is kind of minor, then we can update the factorization efficiently. So not only does it help us to solve many linear systems where the right-hand side changes, we can solve many linear systems where the left-hand side also changes, as long as those changes aren't too drastic. Like a rank 1 change to a, we can handle. If you give me one more row or column to a, we can handle that kind of thing. So we're going to talk about two factorizations only, but there are a lot more. There are, I don't know, 5+ that people probably use. And in terms of the stuff we've talked about so far, it's all fairly, I'd say, standard material. For matrix factorizations and all the stuff I'm talking about for the rest of the lecture, there is the definitive reference, which is a really great reference, is this book called Matrix Computations by Golub and Van Loon. I have it in the references at the end. I really like that book a lot, so I highly recommend that you take a look at it if you want more information about some of this stuff. So if A is a symmetric and positive definite matrix, so it's square, invertible, and it's also symmetric, then it has what we call a Cholesky decomposition, which means that we can always write A as a product of a lower triangular matrix and an upper triangular matrix. Looks like this. Okay? And we can compute this factorization in n cubed flops. Something to remember. It's actually on the order of n cubed over 3. And this book, like I said, it tells you how to do that, although you don't need really to know how to do that in practice, because you would just use your favorite MATLAB tool or R tool to do that for you. Once we have the Cholesky factors, we can solve the linear system very quickly just by performing 2 triangular system solves. Right? We first solve for y equals L inverse times b, by forward substitution. That takes n squared flops. And then we solve for, that should say y, L transpose inverse times y, not b here. It's just a typo. By back substitution, because this matrix is upper triangular, and n squared flops. So computing the factorization takes n cubed. Solving takes n squared once we have it. Together, it takes n cubed plus n squared flops, which is about the cost of what it would have taken us just to do something like Gaussian elimination or just some generic thing for solving this linear system in the first place. But if I told you that you wanted now to solve ax equals b prime, then it would only take you 2 n squared flops if you store the Cholesky of A. Because you already have L and L transpose, you just have to do these 2 triangular system solves. So one interesting context that we're going to talk about is least squares problems. It's a very common setting when people are encountering linear systems. It's pretty classic. Suppose I wanted you to compute the minimizer of the following least squares criterion, right? I wanted you to find the b that made the L2 norm between y and x beta the smallest. Of course, we know that from the normal equations, just by differentiating this and setting it equal to 0, the answer is x transpose x inverse x transpose y, provided that x has full column rank. Okay, how expensive is that if we wanted to use a Cholesky factorization? What would we factorize, first of all? We would factorize x transpose x, which is a p by p matrix, and then we use that to solve the system x transpose x beta equals x transpose y. So we have to compute x transpose y. That costs on the order of p times n flops. We have to compute the Cholesky of x transpose x. That costs on the order of p squared times n flops. So I'm sorry. The Cholesky of x transpose x costs p squared over 3 flops, just like we learned before. Computing x transpose x in the first place costs p squared times n flops. For matrix-matrix multiplication stuff we learned. And then solving the linear system once we have the Cholesky factorization costs on the order of p squared flops. So in total, this costs about n p squared flops plus p cubed flops, or just about n p squared flops if n is much larger than p. The most expensive thing here was actually just computing x transpose x. That would dominate the computational cost if n was much larger than p. Okay, so that's one way to solve least squares problems using the Cholesky factorization. Here is, I'd say, its main competitor. I think that Cholesky and QR are the two things people use the most. Some people may disagree with me. Like I said, there's lots more matrix factorizations. But these, I think, they're nice to know because they have kind of complementary strengths. The QR factorization takes a matrix A, and it decomposes it into a product of an orthogonal matrix with an upper triangular matrix. Once you had this, by the way, what would A transpose A look like if Q had orthogonal columns? A transpose A would be, right? A transpose A, if A was Q times R, it would be R transpose times Q transpose Q times R, which is just R transpose times R, which is L transpose if I just renamed that. So if we have the QR of A, I know a Cholesky for A transpose A. Okay. The computational cost is similar. It takes on the order of, here now it's m n squared flops, but if A was a square, this would be n, that would be n cubed flops. Because here we can actually compute a QR factorization for any rectangular matrix. If you want to put it on the same scale as the Cholesky, just think about it being square, and it costs something like n cubed flops. And to use this to solve linear systems, we use this key identity, which is that if I have any vector x and I ask for its 2 norm, then that's going to be, I can write that as the 2 norm of q transpose x plus q tilde transpose x squared, where I take q and I put next to it q tilde, and these form a square orthogonal matrix O. So this O is going to be M by M. This just comes from the fact that this is just equal to the orthogonal matrix O transpose times x squared. And we always know that, right, the norm of vector is invariant if I multiply it by an orthogonal matrix. So how do I solve least squares problems with the QR decomposition? I use this key identity, and I say that if you want to minimize y minus x beta, and I take a QR of x, then I can multiply everything through by q transpose, right? And I get q transpose times y. This part, where I replaced x with qr, just reduces to r times beta. I also have to do q transpose times all of this, q tilde transpose times all of this, where q tilde was just a set of complementary columns that complete the space. But you'll notice that then that actually cancels out the part that involves beta. So all that's left is q transpose tilde times y. So in other words, this doesn't matter for the minimization over beta. And if I'm solving a least squares problem with the QR decomposition, all I have to do is worry about this part. And now all I have is some vector, call it z, minus r times beta. I want to find the solution to that linear system. And I can do that with a single back substitution because r is upper triangular. So in essence, what we have to do is we have to compute the QR decomposition of q, compute q transpose y, and then just solve this linear system, r beta equals q transpose y. And the flop count comes out to be 2 times n times p squared, roughly on that order, if n is much bigger than or equal to p. Okay? Let's skip this stuff on sensitivity because we're essentially out of time. This is the most important point. When would you use a Cholesky versus a QR? This is something that you would face in practice. And I just wanted to give you the rough guideline for this. If you look back at their computational cost, the QR decomposition took about 2 times n times p squared flops for solving a linear system, and the Cholesky took about n times p squared flops. You can go through the flop counts to check that. So Cholesky is cheaper. You may think you may always want to use it. It also uses less memory because all we're doing is we're storing a product of two. We're actually only restoring one lower triangular matrix, right? Because this is L, and Cholesky is L times L transpose. So all we have to do is store that. So it's both cheaper and uses less memory. What's the caveat? The caveat is that it's actually a lot more sensitive to numerical instability. So if x transpose x is nearly singular, or even it's just poorly conditioned, Cholesky has a lot more potential for kind of numerical error than the QR will. So QR is a lot more stable. So there's a trade-off there. If you want to spend twice as much computation and twice as much memory but get a more accurate solution, you want to use a QR. If you want to be faster, use less memory, and you don't care as much about an accurate solution, then you want to use the Cholesky. Okay? That's essentially the trade-off to keep in mind. And like I said, we're going to revisit these fundamental units for computation. We talk about second-order methods because we'll see that their iteration the number of computations per iteration is really different than we saw for first-order methods. But you want to think about all this stuff in the context of factorizations because they often make your life a lot easier when you're solving linear systems. Okay, that was it. There's some advanced topics here in case you're interested. These are not the only methods that you can use to solve linear systems. I've put down a bunch of advanced topics, and I've even put down some indirect methods, which are a popular topic now in current research. So you don't have to worry about this stuff necessarily in terms of the homework, but I think it's interesting, so go ahead and go through some of the advanced topics if you're interested. Okay, I will see you on Monday. Make sure to remember to turn in your milestone by today at 4. Your project.